Hello, my name is Jacob Sanders, and today I'm going to be reading RFC 791. It's titled Internet Protocol, and I'm going to skip over the table of contents, going to skip over the preface, and I'm going to jump in right here. Internet Protocol. Section 1.1, Motivation. The Internet Protocol is designed for use in interconnected systems of packet-switched computer communication networks. Such a system has been called a catenet. The Internet Protocol provides for transmitting blocks of data called datagrams from sources to destinations, where sources and destinations are hosts identified by fixed-length addresses. The Internet Protocol also provides for fragmentation and reassembly of long datagrams, if necessary, for transmission through small packet networks. Section 1.2, Scope. The Internet Protocol is specifically limited in scope to provide the functions necessary to deliver a package of bits, which is an Internet datagram, from a source to a destination over an interconnected system of networks. There are no mechanisms to augment end-to-end data reliability, flow control, sequencing, or other services commonly found in host-to-host protocols. The Internet Protocol can capitalize on the services of its supporting networks to provide various types and qualities of service. Section 1.3, Interfaces. This protocol is called on by host-to-host protocols in an Internet environment. This protocol calls on local network protocols to carry the Internet datagram to the next gateway or destination host. For example, a TCP module will call on the Internet module to take a TCP segment, including the TCP header and user data, as the data portion of the Internet datagram. The TCP module would provide the address and other parameters in the Internet header to the Internet module as arguments of the call. The Internet module would then create an Internet datagram and call on the local network interface to transmit the Internet datagram. In the ARPANET case, for example, the Internet module would call on a local net module which would add the 1822 leader to the Internet datagram, creating an ARPANET message to transmit to the IMP. The ARPANET address would be derived from the Internet address by the local network interface and would be the address of the same host in the ARPANET. That host might be a gateway to other networks. Section 1.4, Operation. The Internet Protocol implements two basic functions, addressing and fragmentation. The Internet modules use the addresses carried in the Internet header to transmit Internet datagrams toward their destinations. The selection of a path for transmission is called routing. The Internet modules use fields in the Internet header to fragment and reassemble Internet datagrams when necessary for transmission through small packet networks. The model of operation is that an Internet module resides in each host engaged in the Internet communication and in each gateway that interconnects networks. These modules share common rules for interpreting address fields and for fragmenting and assembling Internet datagrams. In addition, these modules, especially in gateways, have procedures for making routing decisions and other functions. The Internet Protocol treats each Internet datagram as an independent entity unrelated to any other Internet datagram. There are no connections or logical circuits, virtual or otherwise. The Internet Protocol uses four key mechanisms in providing its service: type of service, time to live, options, and header checksum. The type of service is used to indicate the quality of the service desired. The type of service is an abstract or generalized set of parameters which characterize the service choices provided in the networks that make up the Internet. This type of service indication is to be used by gateways to select the actual transmission parameters for a particular network. The network to be used for the next hop or the next gateway when routing an Internet datagram. The time to live is an indication of an upper bound on the lifetime of an Internet datagram. It is set by the sender of the datagram and reduced at the points along the route where it is processed. If the time to live reaches 0 before the Internet datagram reaches its destination, the Internet datagram is destroyed. The time to live can be thought of as a self-destruct time limit. The options provide for control functions needed or useful in some situations, but unnecessary for the most common communications. The options include provisions for timestamps, security, and special routing. The header checksum provides a verification that the information used in processing internet datagrams has been transmitted correctly. The data may contain errors. If the header checksum fails, the internet datagram is discarded at once by the entity which detects the error. The Internet Protocol does not provide a reliable communication facility. There are no acknowledgements either end-to-end or hop-by-hop. There is no error control for data, only a header checksum. There are no retransmissions. There is no flow control. Errors detected may be reported via the Internet Control Message Protocol, ICMP, which is implemented in the Internet Protocol module. Section 2, Overview. Section 2.1, Relation to Other Protocols. The following diagram illustrates the place of the Internet Protocol in the protocol hierarchy. Here we have Telnet, FTP, TFTP, and then then we have TCP underneath Telnet and FTP, and we have UDP under TFTP, and then we have Internet Protocol and ICMP underneath TCP and UDP. Although it is suggested here that IP, or the Internet Protocol, is actually what's underneath TCP and UDP, whereas ICMP is underneath some other types of higher level transport and application level protocols. And underneath this is the local network protocol. Internet Protocol interfaces on one side to the higher level host-to-host protocols, and on the other side to the local network protocol. In this context, a local network may be a small network in a building or a large network such as the ARPANET. Section 2.2, Model of Operation. The model of operation for transmitting a datagram from one application program to another is illustrated by the following scenario. We suppose that this transmission will involve one intermediate gateway. The sending application program prepares its data and calls on its local internet module to send that data as a datagram and passes the destination address and other parameters as arguments of the call. The internet module prepares a datagram header and attaches the data to it. The internet module determines a local network address for this internet address. In this case, it is the address of a gateway. It sends this datagram and the local network address to the local network interface. The local network interface creates a local network header and attaches the datagram to it, then sends the result via a local network. The datagram arrives at a gateway host wrapped in the local network header. The local network interface strips off this header and turns the datagram over to the internet module. The internet module determines from the internet address that the datagram is to be forwarded to another host in a second network. The internet module determines a local net address for the destination host. It calls on the local network interface for that network to send the datagram. This local network interface creates a local network header and attaches the datagram, sending the result to the destination host. At this destination host, the datagram is stripped off the local net header by the local network interface and handed to the internet module. The internet module determines that the datagram is for an application program in this host. It passes the data to the application program in response to a system call, passing the source address and other parameters as results of the call. And here we see another diagram where I chose application program, passing information to the internet module, passing information to the LNI1, passing information to the local network 1, which then passes information back up to the LNI1, which passes it to the internet module, which then passes it down to the LNI2, which passes it to the local network, local network 2, which passes it up to the LNI2, which passes it to the internet module, which eventually gets to the other application program. And this is described as the transmission path. Section 2.3, Function Description. The function or purpose of Internet Protocol is to move datagrams through an interconnected set of networks. This is done by passing the datagrams from one Internet module to another until the destination is reached. The Internet modules reside in hosts and gateways in the Internet system. The datagrams are routed from one Internet module to another through individual networks, based on the interpretation of an Internet address. Thus, one important mechanism of the Internet Protocol is the Internet address. In the routing of messages from one Internet module to another, datagrams may need to traverse a network whose maximum packet size is smaller than the size of the datagram. To overcome this difficulty, a fragmentation mechanism is provided in the Internet Protocol. Addressing. A distinction. Let me make sure I didn't miss something here. Right. In the routing of messages from one internet module to another, datagrams may need to traverse a network whose maximum packet size is smaller than the size of the datagram. To overcome this difficulty, a fragmentation mechanism is provided in the Internet Protocol. Addressing. A distinction is made between names, addresses, and routes. A name indicates what we seek, an address indicates where it is, a route indicates how to get there. The Internet Protocol deals primarily with addresses. It is the task of higher level, i.e. host-to-host or application protocols, to make the mapping from names to addresses. The Internet Module maps Internet addresses to local net addresses. It is the task of lower level, i.e. local net or gateways procedures, to make the mapping from local net addresses of routes. Addresses are fixed length of 4 octets, which is 32 bits. An address begins with a network number followed by a local address, called the REST field. There are 3 formats or classes of Internet addresses. In Class A, the high order bit is 0. The next 7 bits are the network, and the last 24 bits are the local address. In Class B, the high order 2 bits are 10. The next 14 bits are the network, and the last 16 bits are the local address. In Class C, the high order 3 bits are 110. The next 21 bits are the network, and the last 8 bits are the local address. Care must be taken in mapping Internet addresses to local net addresses. A single physical host must be able to act as if it were several distinct hosts to the extent of using several distinct Internet addresses. Some hosts will also have several physical interfaces, which is called multi-homing. That is, provision must be made for a host to have several physical interfaces to the network, with each having several logical Internet addresses. Examples of address mappings may be found in address mappings. Fragmentation. Fragmentation of an Internet datagram is necessary when it originates in a local net that allows a large packet size and must traverse a local net that limits packets to a smaller size to reach its destination. An Internet datagram can be marked "Don't Fragment." Any Internet datagram so marked is not to be Internet fragmented under any circumstances. If Internet datagram marked "Don't Fragment" cannot be delivered to its destination without fragmenting it, it is to be discarded instead. Fragmentation, transmission, and reassembly across a local network which is invisible to the Internet Protocol module is called Intranet Fragmentation and may be used. Internet fragmentation and reassembly procedure needs to be able to break a datagram into an almost arbitrary number of pieces that can be later reassembled. The receiver of the fragments uses the identification field to ensure that fragments of different datagrams are not mixed. The fragment offset field tells the receiver the position of a fragment in the original datagram. The fragment offset and length determine the portion of the original datagram covered by this fragment. The more fragments flag indicates, by being reset, the last fragment. These fields provide sufficient information to reassemble datagrams. The identification field is used to distinguish the fragments of one datagram from those of another. The originating protocol module of an Internet datagram sets the identification field to a value that must be unique for the source-destination pair and protocol for the time that the datagram will be active in the Internet system. The originating protocol module of a complete datagram sets the more fragments flag to 0 and the fragment offset to 0. To fragment a long Internet datagram, an Internet Protocol module, for example in a gateway, creates 2 new Internet datagrams and copies the contents of the Internet header fields from the long datagram into both new Internet headers. The data of the long datagram is divided into 2 portions on an 8-octet or 64-bit boundary. The second portion might not be an integral multiple of 8 octets, but the first must be. Call the number of 8-octet blocks in the first portion NFB for number of fragment blocks. The first portion of the data is placed in the first new Internet datagram, and the total length field is set to be the length of the first datagram. The more fragments flag is set to 1. The second portion of the data is placed in the second new Internet datagram, and the total length field is set to be the length of the second datagram. The more fragments flag carries the same value as the long datagram. The fragment offset field on the second new Internet datagram is set to the value of that field in the long datagram plus the NFB, which is the number of fragment blocks. This procedure can be generalized for an n-way split rather than the 2-way split described. To To assemble the fragments of an Internet datagram, an Internet Protocol module, for example at a destination host, combines Internet datagrams that all have the same value for the 4 fields: identification, source, destination, and protocol. The combination is done by placing the data portion of each fragment in the relative position indicated by the fragment offset in that fragment's Internet header. The first fragment will have the fragment offset 0, and the last fragment will have the more fragments flag reset to 0. Section 2.4 Gateways. Gateways implement Internet Protocol to forward datagrams between networks. Gateways also implement the Gateway-to-Gateway Protocol, or GGP, to coordinate routing and other Internet control information. In a gateway, the higher-level protocols need not be implemented, and the GGP functions are added to the IP module. And here we have a figure where the Internet Protocol and ICMP and GGP are all talking to the local network. They're called gateway protocols. Section 3, Specification. Section 3.1, Internet Header Format. A summary of the contents of the Internet header follows. And we have a 32-bit diagram or table where the first 4 bits are version, the next 4 bits are an IHL, the next 8 bits are type of service, and the next 16 bits are total length. The next 16 bits are identification, the next 4 bits are flags, and the next 12 bits are fragment offset. The next 8 bits are time to live, the next 8 bits are protocol, and the next 16 bits are a header checksum. Then we have the next 32 bits being the source address, the next 32 bits being the destination address, and the next 16 bits being options. I guess it's not 16. It looks like 24 bits being options, and the last 8 bits being padding, at which point you lead into the payload for an IP datagram, and it has its own binary interface, right? The total header is what? 32, 64, 128, plus another 64 is it's easier to do it with bytes. So there's 4, 8, 12, 16, 20, 24. I think there's 24 bytes in a IP header. It's called the Internet Datagram header, and now we're going to go through it in detail. The version part is 4 bits in length. The version field indicates the format of the Internet header. This document describes version 4. IHL is 4 bits in length. It's called the Internet header length. It is the length of the Internet header in 32-bit words, and thus points to the beginning of the data. Note that the minimum value for a correct header is 5. Type of service. This is 8 bits. The type of service provides an indication of the abstract parameters of the quality of service desired. These parameters are to be used to guide the selection of the actual service parameters when transmitting a datagram through a particular network. Several networks offer service precedence, which somehow treats high precedence traffic as more important than other traffic, generally by accepting only traffic above a certain precedence at time of high load. The major choice is a 3-way trade-off between low delay, high reliability, and high throughput. Bits 0 to 2 are the precedence. Bits 3 is the normal delay. The value 0 is a normal delay. The value 1 is low delay. Bit 4 is the value 0 is normal throughput. The number 1 is high throughput. Bit 5, the number 0 is normal reliability, and the value of 1 is high reliability. And then the bits 6 to 7 are reserved for future use. And here we see it explained again. And the first 3 bits are the precedence, and then the third bit is DTR00. Okay, so anyways, then we have precedence. 111 equals network control. 110 equals inter-network control, 101 equals critic ECP, 100 equals flash override, 011 equals flash, 010 equals immediate, 001 equals priority, and 000 is routine. The use of delay, throughput, and reliability indications may increase the cost in some sense of the service. In many networks, better performance for one of these parameters is coupled with worse performance on another. Except for very unusual cases, at most two of these three indications should be set. The type of service is used to specify the treatment of the datagram during its transmission through the Internet system. Example mappings of the Internet type of a service to the actual service provided on networks such as AutoDIN2, ARPANET, SATNet, and PRNet is given in service mappings. The network control precedence designation is intended to be used within a network only. The actual use and control of that designation is up to each network. The inter-network control designation is intended for use by gateway control originators only. If the actual use of these precedence designations is of concern to a particular network, it is the responsibility of that network to control the access to and use of these precedence designations. Total length is 16 bits in length. Total length is the length of the datagram, measured in octets, including internet header and data. This field allows the length of a datagram to be up to 65,535 octets. Such long datagrams are impractical for most hosts and networks. All hosts must be prepared to accept datagrams of up to 576 octets, whether they arrive whole or in fragments. It is recommended that hosts only send datagrams larger than 576 octets if they have assurance that the destination is prepared to accept the larger datagrams. The number 576 is selected to allow a reasonably sized data block to be transmitted in addition to the required header information. For example, this size allows a data block of 512 octets plus 64 header octets to fit in a datagram. The maximal internet header is 60 octets, and a typical internet header is 20 octets, allowing a margin for headers of higher level protocols. Identification, 16 bits. An identifying value assigned by the sender to aid in assembling the fragments of a datagram. Flags, 3 bits. Various control flags. Bit 0 is reserved and must be 0. Bit 1 is DF, and a value of 0 equals may fragment, and a value of 1 equals don't fragment. Bit 2 is MF, and a value of 0 equals last fragment, and a value of 1 equals more fragments. Fragment offset. This is 13 bits. This field indicates where in the datagram this fragment belongs. The fragment offset is measured in units of 8 octets, 64 bits. The first fragment has offset 0. Time to live, 8 bits. This field indicates the maximum time the datagram is allowed to remain in the internet system. If this field contains the value 0, then the datagram must be destroyed. This field is modified in internet header processing. The time is measured in units of seconds, but since every module that processes a datagram must decrease the TTL by at least 1, even if it processes the datagram in less than a second, the TTL must be thought of only as an upper bound on the time a datagram may exist. The intention is to cause undeliverable datagrams to be discarded and to be bound to the maximum datagram lifetime. Protocol, 8 bits. This field indicates the next level protocol used in the data portion of the internet datagram. The values for various protocols are specified in assigned numbers. Header checksum, 16 bits. A checksum on the header only. Since some header fields change, e.g. time to live, this is recomputed and verified at each point that the internet header is processed. The checksum algorithm is, the checksum field is the 16-bit 1's complement of the 1's complement sum of all 16-bit words in the header. Okay. For purposes of computing the checksum, the value of the checksum field is 0. This is a simple to compute checksum, and experimental evidence indicates it is adequate, but it is provisional and may be replaced by a CRC procedure depending on further experience. Source address, 32 bits. The source address is basically C section 3.2. Destination address is 32 bits, C section 3.2. Options is variable in length. The options may appear or not in datagrams. They must be implemented by all IP modules on hosts and gateways. What is optional is their transmission in any particular datagram, not their implementation. In some environments, the security option may be required in all datagrams. The option field is variable in length. There may be 0 or more options. There are 2 cases for the format of an option. Case 1, a single octet of option type. Case 2, an option type octet, an option length octet, and the actual option data octets. The option length octet counts the option type octet and the option length octet as well as the option data octets. The option type octet is viewed as having 3 fields. Bit 1 is the copied flag. The next 2 bits are the option class, and the next 5 bits, adding up to a total byte, is the option number. The copied flag indicates that this option is copied into all fragments on fragmentation. Bit value of 0 equals not copied, a bit value of 1 equals copied. The option classes are 0 equals control, 1 equals reserved for future use, 2 equals debugging and measurement, 3 equals reserved for future use. The following internet options are defined. Class, number, length, description is the table, and so class 0, number 0, length, hyphen, end of option list. This option occupies only 1 octet. It has no length octet, no operation. This option occupies, only 1 octet. It has no length octet. This is pretty strange. So the following internet options are defined. Class of 0, number of 2, length of 11 is a security option, and it's used to carry security compartmentation, user group, TCC, and handling restriction codes compatible with DoD requirements. Class 0, number 3 has a variable length, and it's a loose source routing used to route the internet datagram based on information supplied by the source. Class 0, number 9, length variable is a strict source routing used to route the internet datagram based on information supplied by the source. Class 0, number 7, excuse me, sorry, have to multitask here. Specific option definitions. I'm just gonna skip the rest of this. Man, this stuff is so dense. Can you believe that this is what's powering the internet? Just to take a step, like a second, and just think about that, like probably like 99.99% of people have no idea how any of this works. And then even the ones that have a vague notion don't really know about all that much of the like combinations and how complicated it really is. It's crazy, man. Okay, so specific option definitions. End of option list. Type equals 0. This option indicates the end of an option list. This might not coincide with the end of the internet header. According to the internet header length, this is used at the end of all options, not the end of each option, and need only be used if the end of the options would not otherwise coincide with the end of the internet header. It may be copied, introduced, or deleted on fragmentation, or for any other reason. Oh man, they're going to go into each one of these options. I didn't even know these existed. No operation. This is a value of 1. This option may be used between options, for example, to align the beginning of a subsequent option on a 32-bit boundary. It may be copied or deleted for fragmentation. Security. This option provides a way for hosts to send security compartmentation, handling restrictions, and TCC, which is closed user group parameters. The format for this option is as follows. The first octet has, this is just got some binary stuff here, and then I'm not really sure what this other stuff is. The S field is 16 bits, specifies one of the 16 levels of security, 8 of which are reserved for future use. Unclassified, confidential, EFTO, MMM, prog, restricted, secret, top secret, reserved for future use. Compartments, C field, 16 bits. An all zero value is used when the information transmitted is not compartmented. Other values for the compartments field may be obtained from the Defense Intelligence Agency. The H field is handling restrictions. The values for the control and release markings are alphanumeric digraphs and are defined in the Defense Intelligence Agency manual. Transmission control code is a TCC field. It's 14 bits in length. Provides a means to segregate traffic and define control communities of interest among subscribers. This must be copied on fragmentation. This option appears at most once in a datagram. Loose source and record route. The loose source and record route, or LSRR option, provides a means for the source of an internet datagram to supply routing information to be used by the gateways in forwarding the datagram to the destination, and to record the route information. The option begins with the option type code. The second octet is the option length, which includes the option type code, and the length octet, the pointer octet, the length 3 octets of route data. The third octet is the pointer into the route data, indicating the octet which begins the next source address to be processed. The pointer is relative to this option, and the smallest legal value for that pointer is 4. Our route data is composed of a series of internet addresses. Each internet address is 32 bits or 4 octets. If the pointer is greater than the length, the source route is empty and the recorded route is full, and then routing is said to be based on destination and address field. If the address and destination address field has been reached and the pointer is not greater than the length, the next address in the source route replaces the address in the destination address field, and the recorded route address replaces the source address just used, and pointer is increased by 4. The recorded route address is the Internet module's own internet address as known in the environment into which this datagram is being forwarded. This procedure of replacing the source route with the recorded route, though it is in the reverse of the order it must be in to be used as a source route, means the option and the IP header as a whole remains a constant length as the datagram progresses through the internet. This option is a loose source route because the gateway or host IP is allowed to use any route of any number of other intermediate gateways to reach the next address in the route. Must be copied on fragmentation. Appears at once in a datagram. Strict source and record route. This has 3 sections. The first is the type, where it has a value of 137. Then it has length, pointer, and then route data. The strict source and record route SSRR option provides a means for the source of the internet datagram to supply routing information to be used by the gateways in forwarding the datagram to the destination, and to record the route information. The option begins with the option type code. The second octet is the option length, which includes the option type code and the length octet, the pointer octet, and the length 3 octets of route data. The third octet is the pointer into the route data, indicating the octet which begins the next source address to be processed. The pointer is relative to this option, and the smallest legal value for the pointer is 4. Our route data is composed of a series of internet addresses. Each internet address is 32 bits or 4 octets. If the pointer is greater than the length, the source route is empty, and the recorded route full, and the routing is to be based on the destination address field. If the address and destination address field has been reached, and the pointer is not greater than the length, the next address is the source route. The next address in the source route replaces the address in the destination address field, and the recorded route address replaces the source address just used, and the pointer is increased by 4. The recorded route address is the Internet module's own internet address as known in the environment into which this datagram is being forwarded. This procedure of replacing the source route with the recorded route, though it is in the reverse of the order it must be in although it is in the reverse of the order it must be in to be used as a source route, means the option and the IP header as a whole remains a constant length as the datagram progresses through the internet. So this is pretty hard stuff. At least for me, it's pretty hard. I wonder if there's someone, there probably are people out there that just are like way more intelligent than most people and they just can like make sense of everything. But stuff seems pretty hard for me to parse sometimes, where it's like it feels really coin flippy, where it's like, does the word mean this or does it mean that? Because for a while I was pretty confused because I saw the word like header used in like 50 different contexts, like in IP and TCP and HTTP, and I was just like, are these the same? Are these different? And I was like a noob, and I'm still a noob. Alright, so enough self-reflection about how this is. Let's continue going into it. This option is a strict source route because the gateway or host IP must send the datagram directly to the next address in the source route through only the directly connected network indicated in the next address to reach the next gateway or host specified in the route. Must be copied on fragmentation. The record route. Its type value is 7. Like everything else we've seen here, it's got a length, it's got a pointer, it's got route data. I'm still trying to make sense of why this exists. Like, in the IP header, isn't there already like a source address and a destination address? What is this extra information for? Okay, the record route option provides a means to record the route of an internet datagram. The option begins with the option type code. The second octet is the option length, which includes the option type code, and the length octet, the pointer octet, and the length 3 octets of route data. The third octet is the pointer into the route data, indicating the octet which begins the next area to store a route address. The pointer is relative to this option, and the smallest legal value for the pointer is 4. A recorded route is composed of a series of internet addresses. Each internet address is 32 bits or 4 octets. If the pointer is greater than the length, the recorded route data area is full. The originating host must compose this option with a large enough route data area to hold all the address expected. The size of the option does not change due to adding addresses. The initial contents of the route data area must be 0. When an internet module routes a datagram, it checks to see if the record route option is present. If it is, it inserts its own internet address as known in the environment into which this datagram is being forwarded into the recorded route, being at the octet indicated by the pointer, and increments the pointer by 4. If the route data area is already full, if the pointer exceeds the length, the datagram is forwarded without inserting the address into the recorded route. If there is some room but not enough room for a full address to be inserted, the original datagram is considered to be in error and is discarded. In either case, an ICMP parameter problem message may be sent to the source host. Not copied on fragmentation, goes in the first fragment only, appears at most once in a datagram. That kind of makes sense to me. There's some like commands you can run, I forget exactly what they're called, but if you want to be able to, I think it's trace route or something, if you want to trace the entire route that an IP datagram is going, I guess that's what this option is for. It seems weird to have a lot of things sort of bundled inside of this IP layer rather than making them application layer on top of it, or like transport layer. But that's why I'm reading this, because it's eye-opening, right? Alright, so stream identifier. Its type has the value 136, and its length has the value 4, and then it has a stream ID. This option provides a way for the 16-bit SATnet stream identifier to be carried through networks that do not support the stream concept. It must be copied on fragmentation, and it appears once. Internet timestamp. its type is the value 68. It has a length, a pointer, what looks like an outflow option, and then a flag, and then an internet address, and then a timestamp, both of which are 32 bits. The option length is the number of octets in the option, counting the type, length, pointer, and overflow/flag octets, maximum length 40. The pointer is the number of octets from the beginning of this option to the end of timestamps plus 1, i.e. it points to the octet beginning the space for the next timestamp. The smallest legal value is 5. The timestamp area is full when the pointer is greater than the length. The overflow is 4 bits in length, and it is the number of IP modules that cannot register timestamps due to lack of space. The flag is 4 bits. There's only 3 that are used. A value of 0 means timestamps only, stored in consecutive 32-bit words. Value of 1 means each timestamp is preceded with internet address of the registering entity. And a value of 3 is the internet address fields are pre-specified. An IP module only registers its timestamp if it matches its own address with the next specified internet address. The timestamp is a write-justified 32-bit timestamp in milliseconds since midnight UT. If the time is not available in milliseconds or cannot be provided with respect to midnight UT, then any time may be inserted as a timestamp provided the high order bit of the timestamp field is set to 1 to indicate a use of a non-standard value. The originating host must compose this option with a large enough timestamp data area to hold all the timestamp information expected. The size of the option does not change due to adding timestamps. The initial contents of the timestamp data area must be 0 or internet address /0 pairs. Alright, let's continue. If the timestamp data area is already full, the pointer exceeds the length. The datagram is forwarded without inserting the timestamp, but the overflow count is incremented by 1. If there is some room but not enough room for a full timestamp to be inserted, or the overflow count itself overflows, the original datagram is considered to be an error and is discarded. In either case, an ICMP parameter problem message may be sent to the source host. The timestamp option is not copied upon fragmentation. It is carried in the first fragment. Appears at most once in a datagram. Okay, padding, the last thing. It's a variable length, and it's the internet header padding that is used to ensure that the internet header ends on a 32-bit boundary. The padding is 0. Okay. Section 3.2, Discussion. The implementation of a protocol must be robust. Each implementation must expect to interoperate with others created by different individuals. While the goal of the specification is to be explicit about the protocol, there is the possibility of differing interpretations. In general, an implementation must be conservative in its sending behavior and liberal in its receiving behavior. That is, it must be careful to send well-formed datagrams, but must accept any datagram that it can interpret. The basic internet service is datagram-oriented and provides for the fragmentation of datagrams at gateways, with reassembly taking place at the destination internet protocol module in the destination host. Of course, fragmentation and reassembly of datagrams within a network or by private agreement between the gateways of a network is also allowed, since this is transparent to the internet protocols and the higher level protocols. This transparent type of fragmentation and reassembly is termed network-dependent or intranet fragmentation. Intranet, and fragmentation, network-dependent fragmentation, and is not discussed further here. Internet addresses distinguish sources and destinations to the host level and provide a protocol field as well. It is assumed that each protocol will provide for whatever multiplexing is necessary within a host. Addressing. To provide for flexibility in assigning address to networks and allow for the large number of small to intermediate sized networks, the interpretation of the address field is coded to specify a small number of networks with a large number of hosts, a moderate number of networks with a moderate number of hosts, and a large number of networks with small number of hosts. In addition, there is an escape code for extended addressing mode. Address format. High order bits. High order bits are either 0, 10, 110, or 111. If it's 0, then the format is 7 bits of net and 24 bits of host, and it's called a class A address. If it's 1, 0, if the higher order bits are 1, 0, and then the format is 14 bits of net and 16 bits of host, and it's called a class B address. If the higher order bits are 1, 1, 0, then it's 21 bits of net and 8 bits of host, and the class is called a class C address. And if it's 111, it's escape to extended addressing mode. A value of 0 in the network field means this network. This is only used in certain ICMP messages. The extended addressing mode is undefined. Both of these features are reserved for future use. The actual values assigned for network addresses is given in assigned numbers. The local address assigned by the local network must allow for a single physical host to act as several distinct internet hosts. That is, there must be a mapping between internet host addresses and network host interfaces that allows several internet addresses to correspond to one interface. It must also be allowed for a host to have several physical interfaces and to treat the datagrams from several of them as if they were all addressed to a single host. Address mappings between internet addresses and addresses for ARPANET or ARPANET, SATNET, PRNet, and other networks are described in address mappings. Fragmentation and reassembly. The Internet Identification field, or ID, is used together with the source and destination address and the protocol fields to identify datagram fragments for reassembly. The more fragments flag bit, MF, is set if the datagram is not the last fragment. The Fragment Offset field identifies the fragment location relative to the beginning of the original unfragmented datagram. Fragments are counted in units of 8 octets. The fragmentation strategy is designed so that an unfragmented datagram has all 0 fragmentation information. MF equals 0, fragment offset equals 0. Take a break for a second. So to pause and have some self-reflection again, let's remind ourselves, we're doing this because if you're like me, you have like this kind of insatiable curiosity, and you're not really that satisfied with the explanations that are given. And what you find out if you embark on this kind of exploration that I'm currently doing and uploading to YouTube in such a unrefined, raw way, where there's going to be all sorts of blemishes that are unavoidable in some ways because people are seeing me in such a real-time, unprocessed or perfected form. But the point is that everyone knows this probably, but there's that deep curiosity of trying to figure out how things actually work and not being satisfied with a more simple and high-level explanation, which is still maybe difficult to grasp, but significantly simpler. But just knowing kind of deep down that it's probably not the actual baseline truth, and having that sort of cognitive dissonance where you're like pretending like you understand how something is when you don't. And then you come and actually read something that's like one of the most detailed forms of a specification for something, and you start to realize just how much has been ignored. And what's hard to notice, what's hard to say about something like this as well is like how much of this information is actually really important or kind of just neglected. Because just because the entire protocol has all this functionality in it, how much of it is actually used, right? Like, and I don't know. That's like a whole other thing. You would have to look at other things like you would have to find that information from somewhere else. All right, so enough of that. We want to be the best programmer we can, and we're not satisfied with the low-hanging fruit approach. Otherwise, I just throw in the towel and go and read some blog post about how the IP protocol does like one thing, and I'd move on. But let's continue instead. If an internet datagram is fragmented, its data portion must be broken on 8 octet boundaries. This format allows 2 to the 13th, or 8,192 fragments of 8 octets, each for a total of 65,536 octets. Note that this is consistent with the datagram total length field. Of course, the header is counted in the total length and not in the fragments. When fragmentation occurs, some options are copied, but others remain with the first fragment only. Every internet module must be able to forward a datagram of 68 octets without further fragmentation. This is because an internet header may be up to 60 octets. Okay, this is because an internet header may be up to 60 octets and the minimum fragment is 8 octets. Every internet destination must be able to receive a datagram of 576 octets either in one piece or in fragments to be reassembled. The fields which may be affected by fragmentation include 1. The options field, 2. The more fragments flag, 3. The fragment offset, 4. The internet header length field, 5. The total length field, and 6. The header checksum. If the don't fragment flag bit is set, then internet fragmentation of this datagram is not permitted, although it may be discarded. This can be used to prohibit fragmentation in cases where the receiving host does not have sufficient resources to reassemble internet fragments. One example of use of the don't fragment feature is to downline load a small host. That's strange, but okay. A small host could have a bootstrap program that accepts a datagram, stores it in memory, and then executes it. The fragmentation and reassembly procedures are most easily described by examples. The following procedures are example implementations. Here, general notation in the following pseudo programs equals. Okay, we've got less than or equal. We've got pound sign, which means not equal. We have an equal, which means equal. We have an arrow, which means is set to. And then we have x to y, which is meant to be read as includes x and excludes y. For example, 4 to 7 would include 4, 5, and 6, but not 7. An example fragmentation procedure. The maximum size datagram that can be transmitted through the next network is called the maximum transmission unit, or MTU. If the total length is less than or equal the maximum transmission unit to the maximum transmission unit, then submit this datagram to the next step in datagram processing. Otherwise, cut the datagram into 2 fragments, the first fragment being the maximum size and the second fragment being the rest of the datagram. The first fragment is submitted to the next step in datagram processing, while the second fragment is submitted to this procedure in case it is still too large. They explain some of the notation here. FO stands for fragment offset, IHL stands for internet header length, DF stands for don't fragment flag, MF stands for more fragments flag, TL stands for total length, OFO stands for old fragment offset, OIHL stands for old internet header length, OMF stands for old more fragments flag, OTL stands for old total length, NFB stands for number of fragment blocks, MTU stands for maximum transmission unit. And now they're going to describe a procedure with these things. I'm going to convert them into what they are in English. So if the total length is less than or equal to the maximum transmission unit, then submit this datagram to the next step in datagram processing. Otherwise, if the data, if the don't fragment flag equals 1, then discard the datagram. And finally, if the total length is greater than the maximum transmission unit, then you're going to have to split it. And so to produce the first fragment, you're going to copy the original internet header. And that's the first step. The second step is you're going to put the internet header length into the old internet header length. Then you're going to copy the total length and put it into the old total length. Then you're going to copy the fragment offset and put it into the old fragment offset, and you're going to copy the more fragments flag into the old more fragments flag. Then you're going to basically calculate the number of fragment blocks by subtracting from the maximum transmission unit the internet header length times 4. Then you're going to take this number and you're going to divide it by 8. And that's going to give you the number of fragment blocks. To understand this math, the reason the internet header length is being multiplied by 4 is because the internet header length itself is a 32-bit value. So because it's 32 bits, each number, because the unit is 32 bits, that's equivalent to 4 bytes. And we need to store basically a number of 64 or 8-byte values in the NFB, right? So this might not be clear again, but the reason you divide by 8 is because 1 NFB is equal to 8 bytes, okay? And the reason you multiply by 4 against the IHL, or the internet header length, is because 1 internet header length equals 4 bytes. And you take the MTU, which in this example is already in bytes, and so when you subtract bytes from bytes and then divide by 8, you're going to get 64, I think it's 64, yeah, 64 bit units, which is what the number of fragment blocks is. Okay, step 4, attach the first NFB times 8 data octets. So number of fragment blocks times 8 data octets. Okay. Yeah, I'm not exactly sure what this is, since my understanding of an NFB is a 8-byte structure. If you take an 8-byte structure and multiply it times 8, you're going to get like a 64, or like you're going to get 8-byte structures, which is going to be 64 bytes in total or something. But my math is probably wrong here. Alright, we'll just keep moving on. Step 5, correct the header. Okay, so conceptually you have to correct the header because you're splitting the original data frame, right? And so its length isn't going to be correct anymore. And so first of all, you're going to set to the more fragments flag, you're going to set that to 1 because it's been fragmented, and so you have to set that flag. But to calculate the total length, you're going to use the internet header length. Okay, so once again, total length is going to be in bytes, and then the internet header length is 32 is a 32-bit bit unit, so you need to multiply it times 4 to convert it to bytes. And then the NFB is a 8-byte unit, so you need to multiply it times 8 because it's a 64-bit to get it in bytes. And so when you add them all together, you'll get the total length in bytes. Then you need to recompute the checksum. Oh, I see. I get why this is happening now. In step 4, they say attach the first NFB times 8 data octets because NFB is of a unit 8 bytes. So to convert it to bytes, which is what an octet is, you have to multiply it times 8 again. Yeah, okay. Step 6, submit this fragment to the next step in datagram processing. So conceptually, the way you can understand this is you have a maximum transmission unit. You always have to have an internet header. And so what you're going to do first is you're going to subtract the length of the internet header from the maximum transmission unit. And then this value is going to be in bytes because that's what it is. And you have to divide it by 8 because the number of fragment blocks is going to be in terms of 64 bits or 8 bytes. So the number of fragment blocks is basically how many bytes you can fit in after you subtract the internet header length. It's so confusing because all of these different lengths aren't just a byte. It would be so obvious if it was just a byte. You want to know what the math would look like, but you can't do it that way because then you lose a lot of representational power. But what it would look like is it would be NFB is equal to MTU minus IHL. That's it. And you would take the total length would be equal to IHL plus NFB. But what it's really saying here is just like the internet header plus its payload, right? Basically. But it's just so much more complicated because the internet header's length is calculated in 16-bit units and the regular payload is calculated in 64-bit units, and neither of those are actually 8-bit units, which is what a byte is, which is what the total length is calculated in. You got to wonder why the total length isn't calculated in something larger. You know, like there's probably some trade-off with that because then you have to do like padding and stuff like that or something. Anyways, that's to get the first datagram. That's part of the that's being fragmented, and then when you produce the second one, you're going to copy some of the internet header. Basically, some of the options aren't copied, and then you're going to append the remaining data. And then you're going to correct the header in the same way. You just have to recalculate this stuff, right? Adding the remaining data is exactly the same as this algorithm. You subtract the internet header and what's from the maximum transmission unit, and then that becomes the NFB, and then you attach that to the end, and then you basically change the values in the internet header so that it has the right, length and stuff like that. And then what you do is so you've corrected the header. Okay. Yeah, okay. They have, as part of the step of correcting the header, you recalculate the internet header length, which makes sense, the total length, and the fragment offset. And then finally, you recompute the checksum because it's going to be different because it's been fragmented. And then you're going to submit this fragment to the fragmentation test, and then you're done. In the above procedure, each fragment except the last was made the maximum allowable size. An alternative might produce less than the maximum size datagrams. For example, one could implement a fragmentation procedure that repeatedly divided large datagrams in half until the resulting fragments were less than the maximum transmission unit size. An example reassembly procedure. For each datagram, the buffer identifier is computed as the concatenation of the source, destination, protocol, and identification fields. If this is a whole datagram, that is, both the fragment offset and more fragments field are 0, then any reassembly resources associated with this buffer identifier are released and the datagram is forwarded to the next step in datagram processing. If no other fragment with this buffer identifier is on hand, then reassembly resources are allocated. The reassembly resources consist of a data buffer, a header buffer, a fragment block bit table, a total data length field, and a timer. The data from the fragment is placed in the data buffer according to its fragment offset and length, and bits are set in the fragment block bit table corresponding to the fragment blocks received. If this is the first fragment, that is, the fragment offset is 0, this header is placed in the header buffer. If this is the last fragment, that is, the more fragments field is 0, the total data length is computed. If this fragment completes the datagram, tested by checking the bits set in the fragment block table, then the datagram is sent to the next step in datagram processing. Otherwise, the timer is set to the maximum of the current timer value and the value of the time to live field from this fragment, and the reassembly routine gives up control. If the timer runs out and all reassembly resources for this buffer identifier are released. The initial setting of the timer is a lower bound on the reassembly waiting time. This is because the waiting time will be increased if the time to live in the arriving fragment is greater than the current timer value, but will not be decreased if it is less. The maximum this timer value could reach is the maximum time to live, approximately 4.25 minutes. The current recommendation for the initial timer setting is 15 seconds. This may be changed as experience with this protocol accumulates. Note that the choice of this parameter value is related to the buffer capacity available and the data rate of the transmission medium. That is, data rate times timer value equals buffer size. And they have an example of this. Notation. Again, we have fragment offset being FO, we have internet header length being IHL, we have more fragments flag being MF, we have TTL for time to live, we have NFB for the number of fragment blocks, we have TL for total length, we have TDL for total data length, we have buff ID for buffer identifier, we have receive bit table for fragment receive bit table, and we have TLB for timer lower bound. And then the procedure is defined here. Step 1, we take the source ID, destination protocol, and identification and put it in the buffer ID. Yeah, I think what this is saying is it's concatenating it. It makes sense, I think. Because based on whether you have the source, basically this is going to be unique for every single connection, and you're going to need a different buffer for each one of these things, because you have to make sure basically the whole point of this is to collect datagrams that are going to the same place, right? And so the same place is this source destination protocol identification. Anyways, so if the fragment offset is 0 and the more fragments is 0, which means this is the first frame in the entire fragmentation, then what you're going to do is, if the buffer with buff ID is allocated, you're going to flush all reassembly for this buff ID. So I guess you're just going to basically delete it. And I don't know what they mean by flush exactly, but then you're going to submit datagram to the next step. Oh wait, my bad. This doesn't mean that it's like the first frame. This means that it's like a frame that's not even split, okay? So if it's not split, you basically just put it in the buffer and then you send it downstream to like the next function or whatever program. Okay, so if no buffer with buff ID is allocated, this is the case where it's like, this is the first time they've received this whole IP, then you're going to allocate the reassembly resources, which is probably going to be the bit table and the header length or the header buffer and then the other thing or whatever. And then what you're going to do, then you're going to allocate reassembly resources with buff ID, and you're going to put the TLB, which is the timer lower bound, into the timer variable. You're going to put 0 into the total data length. Then you're going to, for step 8, this is still if there's basically, okay. For step 8, you're going to put data from fragment into data buffer. Yeah, okay. And then the buffer ID from octet of the fragment offset times 8 to octet of the total length minus. So I'm not really sure about this. And I'm not really sure set receive bits from FO to FO plus that. If more fragments equals 0, then just put that in there. If fragment offset equals 0, then put header and header buffer. Total okay, so this is notably difficult for me to read, partly because I'm not exactly sure what this, like, how these if-elses are working. Because this has, like, the indentation with this is, like, so much different than the other stuff. But whatever, I'm going to keep moving on. This is pretty difficult, but this is, you can look at this if you want and try and make sense of it. I might try and do that later. I'm just going to keep going on though. In the case that two or more fragments contain the same data, either identically or through a partial overlap, this procedure will use the more recently arrived copy in the data buffer and datagram delivered. Identification. The choice of the identifier for a datagram is based on the need to provide a way to uniquely identify the fragments of a particular datagram. The protocol module assembling fragments judges fragments to belong to the same datagram if they have the same source, destination protocol, and identifier. Yeah, that's what I was saying earlier. It's like their UUID in terms of, like, buffers. Thus, the sender must choose the identifier to be unique for this source, destination pair, and protocol for the time the datagram or any fragment of it could be alive in the internet. It seems then that a sending protocol module needs to keep a table of identifiers, one entry for each destination it has communicated with the last maximum packet lifetime for the internet. However, since the identifier field allows 65,536 different values, some hosts may be able to simply use unique identifiers independent of destination. It is appropriate for some higher level protocols to choose the identifier. For example, TCP protocol modules may retransmit an identical TCP segment, and the probability for correct reception would be enhanced if the retransmission carried the same identifier as the original transmission, since fragments of either datagram could be used to construct a correct TCP segment. Type of service. The type of service, or TOS, is for Internet Service Quality Selection. The type of service is specified along the abstract parameters precedence, delay, throughput, and reliability. These abstract parameters are to be mapped into the actual service parameters of the particular networks the datagram traverses. An independent measure of the importance of this datagram, or precedence, that's the definition for it. Delay. Prompt delivery is important for datagrams with this indication. Throughput, high data rate is important for datagrams with this indication. Reliability, a higher level of effort to ensure delivery is important for datagrams with this indication. For example, the ARPANET has a priority bit and a choice between standard messages, which are type 0, and uncontrolled messages, which are type 3. The choice between a single packet and a multi-packet messages can also be considered a service parameter. The uncontrolled messages tend to be less reliably delivered and suffer less delay. Suppose an internet datagram is to be sent through ARPANET. Let the internet type of service be given as precedence 5, delay 0, throughput 1, reliability 1. In this example, the mapping of these parameters to those available for the ARPANET would be to set the ARPANET priority bit on, since the internet precedence is the upper half of its range. To select standard messages, since the throughput and reliability requirements are indicated and delay is not. More details are given on service mappings and service mappings. Time to live. Time to live is set by the sender of the maximum time the datagram is allowed to be in the internet system. If the datagram is in the internet system longer than the time to live, then the datagram must be destroyed. This field must be decreased at each point that the internet header is processed to reflect the time spent processing the datagram. Even if no local information is available on the time actually spent, the field must be decremented by 1. The time is measured by units of seconds, i.e., the value 1 means 1 second. Thus, the maximum time to live is 255 seconds, or 4.25 minutes. Since every module that processes a datagram must decrease the TTL by at least 1, even if it processes, by at least 1, even if process the datagram in less than a second. So they've just got some misspellings or missing words sometimes. I've noticed that earlier. The TTL must be thought of only as an upper bound on the time a datagram may exist. The intention is to cause undeliverable datagrams to be discarded and to bound the maximum datagram lifetime. Some higher level reliable connection protocols are based on assumptions that old duplicate datagrams will not arrive after a certain time elapses. The TTL is a way for such protocols to have an assurance that their assumption is met. Options. The options are optional in each datagram but required in implementations. That is, the presence or absence of an option is the choice of the sender, but each Internet module must be able to parse every option. There can be several options present in the option field. The options might not end on a 32-bit boundary. The Internet header must be filled out with octets of zeros. The first of these would be interpreted as the end of options option, and the remainder as Internet header padding. Every Internet module must be able to act on every option. The security option is required if classified, restricted, or compartmented traffic is to be passed. Checksum. The Internet header checksum is recomputed if the Internet header is changed. For example, a reduction of the time to live, additions or changes to Internet options, or due to fragmentation. This checksum at the Internet level is intended to protect the Internet header fields from transmission errors. There are some applications where a few data bit errors are acceptable while retransmission delays are not. If the Internet protocol enforced data correctness, such applications could not be supported. Errors. Internet protocol errors may be reported via the ICMP messages. Section 3.3. Interfaces. The functional description of user interfaces to the IP is, at best, fictional, since every operating system will have different facilities. Consequently, we must warn readers that different IP implementations may have different user interfaces. However, all IPs must provide a certain minimum set of services to guarantee that all IP implementations can support the same protocol hierarchy. This section specifies the functional interfaces required of all IP implementations. Internet protocol interfaces on one side of the local network and on the other side to either Internet protocol interfaces on one side to the local network and on the other side to either a higher level protocol or an application program. In the following, the higher level protocol or application program or even a gateway program will be called the user since it is using the Internet module. Since Internet protocol is a datagram protocol, there is minimal memory or state maintained between datagram transmissions, and each call on the Internet protocol module by the user supplies all information necessary for the IP to perform the service requested. An example upper-level interface. The following two example calls satisfy the requirements for the user to Internet protocol module communication. Equals arrow means returns. So you send, then they have like a send function with the source destination protocol, a type of service, time to live, buffer pointer, length, ID, do fragment, flag, and then option. And this returns a result where source is the source address, destination is the destination address, protocol is the protocol, TOS is the type of service, TTL is the time to live, buff pointer is the buffer pointer, lem is the length of the buffer, ID is the identifier, DF is don't fragment, opt is option data, and result equals the response. OK equals datagram sent OK, error equals error in arguments or local network error. Note that the precedence is included in the type of service and the security compartment is passed as an option. Okay, and then you have the opposite, which is receive, and you pass it a buff pointer, proto, and it returns a result, source, destination, type of service, length, and option. Everything is the same. When the user sends a datagram, it executes the send call, supplying all the arguments. The Internet Protocol module, on receiving this call, checks the arguments and prepares and sends the message. If the arguments are good and the datagram is accepted by the local network, the call returns successfully. If either the arguments are bad or the datagram is not accepted by the local network, the call returns unsuccessfully. On unsuccessful returns, a reasonable report must be made as to the cause of the problem, but the details of such reports are up to individual implementations. When a datagram arrives at the Internet Protocol module from the local network, either there is a pending receive call from the user addressed or there is not. In the first case, the pending call is satisfied by passing the information from the datagram to the user. In the second case, the user addressed is notified of a pending datagram. If the user addressed does not exist, an ICMP error message is returned to the sender, and the data is discarded. The notification of a user may be via a pseudo interrupt or similar mechanism, as appropriate in the particular operating system environment of the implementation. A user's receive call may then either be immediately satisfied by a pending datagram, or the call may be pending until a datagram arrives. The source address is included in the send call in case the sending host has several addresses, multiple physical connections, or logical addresses. The Internet module must check to see that the source address is one of the legal addresses for this host. An implementation may also allow or require a call to the Internet module to indicate interest in or reserve exclusive use of a class of datagrams, e.g. all those with a certain value in the protocol field. This section functionality characterizes a user IP interface. The notation used is similar to most procedure of function calls in high-level languages, but this usage is not meant to rule out trap-type service calls, e.g. SVCs, UUOs, EMTs, or any other form of inter-process communication. It's crazy because, I've never heard of any of those inter-process communication service calls. And Alright, anyways. Cool, so we got through a lot. We're at the Appendix A, Examples and Scenarios. Example 1. This is an example of the minimal data carrying Internet datagram. It shows the bit table, the 32-bit table again, where version equals 4, Internet header length equals 5. Remember, it's 5 times 32 bits, so it's 20 bytes. And we can calculate this too. Is the header 20 bytes? Let's look. It should be 5 rows then. 1, 2, 3, 4, 5. 5 rows. Bam. That's how it's calculated. Okay, then we have type of service. We have total length equals 21. And this is an integer value for 21, but represented in a 16-bit number, right? Which is really obvious. It's just a 16-bit number. The identification number equals 111, which is interesting. The flag is 0. The fragment offset is 0. The time is 123. The protocol is 1. The header checksum is 16 bits. The source address is 32 bits. Destination address is 32 bits. Data is, in this case, 8 bits. Example Internet datagram. Yeah. Note that each tick mark represents a bit. This is an Internet datagram in version 4 of Internet Protocol. The Internet header consists of 5 32-bit words, and the total length of the datagram is 21 octets. 21. That's true, because the data is only 1 octet. It's like a single ASCII char. This datagram is a complete datagram, not a fragment. Example 2. In this example, we show first a moderate-sized Internet datagram, which is 452 data octets, then 2 Internet fragments that might result from fragmentation of this datagram if the maximum size transmission allowed were 280 octets. Alright, we've got the exact same header information except the total length is 472. And they represent the data basically with just, some extra rows. The Internet header length is still just 20 bytes. Now they're gonna fragment and show that. Now the first fragment that results from splitting the datagram after 256 data octets. Okay, so he basically said that the MTU is 280 octets, 280 bytes, and so this datagram is 452 bytes. So what you're going to do is take the maximum transmission unit of 280 and basically subtract the Internet header, which is 20 from it, so that'll be 260. and then you're going to take those 260 bytes and you're going to put them into the data, right? And 32, 64. Okay. Then they're going to show the second. So he says, now the first fragment that results from splitting the datagram after 256 data octets. Okay, so the maximum transmission unit is 280, but that means you actually only send 276. And that's because if you added, it has to be... I'm not sure why you do it like that, and why you don't do 280. Yeah, I get it. It's probably because it has to be like basically divisible by 32 or something. I don't know. And then they show the next one. It's the same thing basically, but it's split, and the things to pay attention to are probably some of the bit flags. The fragment offset is set. Yeah. To 32 times 8, right? Right. Okay. Here we show an example 3. Here we show an example of a datagram containing options. I'm sort of curious about this. So you got a regular, it's not a regular internet header length. The internet header length is much larger, notably because options are being included, right? And Appendix B, data transmission order. The order of transmission of the header and data described in this document is resolved to the octet level. Whenever a diagram shows a group of octets, the order of transmission of those octets is the normal order in which they are read in English. For example, if the following diagram of octets are transmitted in the order they are numbered. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Whenever an octet represents a numeric quantity, the leftmost bit in the diagram is the highest order or most significant bit. That is, the bit labeled 0 is the most significant bit. For example, the following diagram represents the value 170 in decimal. Similarly, whenever a multi-octet field represents a numeric quantity, the leftmost bit of the whole field is the most significant bit. When a multi-octet quantity is transmitted, the most significant octet is transmitted first. Glossary 1822 BBN report, the specification of the interconnection of host and IMP. ARPANET leader, ARPANET message, unit of transmission between a host and an IMP is in the ARPANET. The maximum size is 1012 octets. ARPANET packet, destination. GGP is gateway to gateway protocol. IMP is the interface message processor. Local address is the address of a host within a network. The actual mapping of an internet local address onto the host addresses in a network is quite general, allowing for many-to-one mappings. Octet is an 8-bit byte. Padding. The internet header padding field is used to ensure that the data begins on a 32-bit word boundary. The padding is 0. I'm reading over a bunch of these in my head, but I'm not saying them because they've already been said like a bazillion times. And we've got a bunch of references. Dang. All right. Made it through. That was hard. I feel like I have a slightly better grasp on how it works. The important thing here, from my point of view, is the reason we're looking at these protocol specifications is not so that we know a bunch of random trivia about a single one of them. It's so that we can see what the ubiquitous tools and solutions and problem solving people employ. So I think that there's limited value. There's still value in just understanding how something like the Internet Protocol works on its own. But I think the real value is to read about the Internet Protocol and like 20 other protocols and to see how they all solve the same problems, right? With computer tools, like basically bits, right? Bits and then procedures on those bits. And really interesting to at least that's what I'm looking for. I don't plan on like implementing any of this stuff ever. And so, but I'm also not just reading stuff for trivia. I don't want to just be able to say random stuff like this at like a party with a bunch of CS people or something. I mean, although that would be kind of, I guess, some sort of orthogonal advantage, the real thing is that if you look at enough of it, you'll see what's actually the real meat and potatoes of all of this stuff. I don't want to speak to that yet because I feel like I'm just at the beginning of this, but I think at some point in time I'll have seen enough of these examples to be able to say like, this is a pattern that exists in almost all protocols. This is just a really ubiquitous computer science tool or solution. So anyways, thanks for listening. As I always say, my channel is not like candy. My channel is like nutrient-packed broccoli. And so it's not going to probably be the most popular channel, or, it's probably not going to be popular at all. But what it is going to be is full of high resolution, very detailed, super relevant and significant things that kind of just get overlooked and ignored by the majority of computer science people who aren't like super hardcore. Now, I think that there are a lot of people out there that are really smart and have a whole lot of knowledge, way more than me. But I think that, this is part of the reason why you go through this stuff is because, it's, well, at least for me, I'm trying to become the best programmer I can. So it makes complete sense for me. But if you want to keep joining me, I'm going to be doing this stuff for as long as I feel compelled to. Sometimes I just stop doing stuff randomly. But yeah, I'm going to be reading a bunch more of these, so you can look at some of my other videos. And like I always say, I give my plug at the very end. I have a blog that I programmed everything for, that I host, on cloud, that I paid for, that I got the TLS certs for. At some point in time, I'll probably do some videos about how to set up a website the way I have, and why it's like one of the coolest things. But you should go check out my blog on programming at pieharbor.com. It's pretty obvious it's the name of this channel as well. I'll probably be making some other websites too that I might kind of start sharing and sort of presenting. But anyways, it's been a blast, so